Okay, this is problem 923. It's on page 499. Carbon steel balls with properties given there. They give us the density, thermal conductivity, heat capacity, and thermal diffusivity. 8 millimeters in diameter are annealed by heating them first to 900 degrees Celsius in a furnace and then allowing them to cool slowly to 100 degrees Celsius in ambient air at 35 degrees Celsius. If the average heat transfer coefficient is 75 watts per square meter per degree Celsius, determine how long the annealing process will take. If 2,500 balls are to be annealed per hour, determine the total rate of heat transfer from the balls to the ambient air. All right, let's make a picture of what they've told us. Basically, there's a furnace, and that furnace has balls coming out of it that have been annealed, or they've been heated so they can be annealed. The initial temperature of the balls was how much? 900 degrees Celsius. Would you want to touch it? Of course not, right? Unless you want to get burned.
I'll be very close to it.
Yeah, they should be giving off a decent amount of radiant energy as well, right? So, you know, if it's winter outside, that might be nice to rub your hands, you know, get nice and toasty close to them, right? You wouldn't want to touch them, but you could get close to them and get some heat off of them. Now, they gave us a number that was 75 watts per square meter per degree Celsius. What kind of symbol should I put with that? It was a property of the air.
It is the average heat transfer coefficient.
Right, so what symbol do we use for that? What letter?
H. Where's the,
H.
where we get the 75 from?
It's in the problem
It's in
statement.
the-
Never, I was reading all
Okay. Now, they gave us a bunch of information about the steel ball, so let's just go ahead and write that down. Density, 7833 kilograms per cubic meter. Thermal conductivity, K, 54 watts per meter per degree Celsius. And heat capacity, CP, 0.465 kilojoules per kilogram per degree Celsius, or per Kelvin, it doesn't matter. Oh, they also gave us thermal diffusivity, alpha, 1.474 times 10 to the negative 6 square meters per second. So these were all just properties of the steel itself. Okay? There were 4 properties given there. Now, they told us the temperature of the air was, let's see, let me put it up here since I've got the air over kind of by itself. The temperature of the air was given as 35 degrees Celsius, but what temperature, this is a very special temperature, what symbol do we usually give this, the temperature of the fluid that the body's immersed in? Infinity, that's right. So this is T infinity. That's the temperature of the fluid with which the body is exchanging heat. Okay? Now, eventually the balls are going to come down this line, and eventually they're going to end up at a temperature of 100 degrees Celsius. What temperature is this? When you recognize Ti and T infinity, well, what temperature is this?
Your T over time, right?
Time. Temperature is a function of time, that's right. This is the temperature at whatever time. Now, we don't know how long it takes to get from here to here, right? We don't know T, this little t, but we do know the temperature once it reaches that point. And our question is, how long does it take? How much time does it take? So that's what we're going to find out. Okay? So, let's start off and ask the question, can we use lumped parameter analysis to do this? Let's find out. Now, how do we decide whether or not we can use lumped parameter analysis? Calculate the BO number, that's right. So let's calculate the BO number. The BO number is HLC over K. So I'm going to use H diameter over 6 over K. Does everyone understand why I'm using diameter over 6? You can say, well, wait a second. I thought for the sphere we used radius. What's going on? We have not chosen yet that we're going to use the transient models, the sphere or the wall or the cylinder, right? We haven't made that determination yet. We have to do this first. Then if we decide that we're going to model these as a sphere using those tables, then we'll use the radius as in the BO number as the characteristic length, okay? So this is the decision before we get to that point. Okay? So, when you plug in all the numbers, it'll come out dimensionless. I won't belabor the point. This comes out to 1.8 times 10 to the negative third, and it's non-dimensional. What was the criteria for using non-dimensional analysis? What was the criteria? Do you remember?
BI is greater, is less than or equal to 0.1.
Is this less than 0.1? By far. So what does it tell us? Can we use lump parameter analysis? So now I realize I messed up. I was thinking we were going to use the models with this, but lump parameter analysis will work. So let's go through lump parameter analysis first, and then let's go through the other models and see how close we get. Why not? Let's try both.
Should they be similar numbers if we use lump parameter versus
Yeah.
the?
They should be. It's just that the other models should be more accurate because they take into account the fact that these round steel balls will not be uniform temperature. They'll be close. So we should get roughly the same number with both methods. That means we're going to use the rest of the class time to do it. Because it's going to take a little bit of time.
For that H in the BO number, did you use 75?
Yes, I did.
Okay,
Sure did. So this H is 75. The K, notice, is a material property of the steel, and the diameter is just the geometry. Okay, so we can use lump parameter analysis. Great. So what does that mean? Well, that means that this equation should be reasonably accurate. It should work well enough for us. We don't have to go through all the mess of the spherical model that we developed, right? But we'll do that as well just because well, I guess because I'm doing it. I don't know. Okay. So let me move this over here so I have a little bit more space. Temperature is a function of time, and that's what we'd like to find. And since what we want to find is this time, t, let's solve for it. In the interest of time in our class, I'm just going to show you the result. It's just math. I think you guys can do this. If you can't, come see me. I'll help you with it. Okay, so there it is. All I did was I solved for time t. To do it, you take the natural log of both sides. That gets rid of the e. Divide by negative b. You're there. Okay. Now remember that we need to calculate that parameter b. Now b is not the BO number. These are different things. But it looks a lot like the BO number because it has the convective heat transfer coefficient, the area A, the density, the volume, and the heat capacity in it. So it kind of looks like the BO number, but it's not. Now, to further confuse you, or to help you or something, volume over area is just a characteristic length, right? Remember, we've already calculated the characteristic length for a sphere. So basically what I'm going to do for this is plug in 6 over d. Remember, it was d over 6? For a sphere, we discovered that the volume per area, which is the characteristic length, was d over 6. Remember, we showed that a minute ago. Well, here we're going to use it. Since we have a over v, I'm just going to use 6 over d in the equation. Okay? So basically, to simplify this just a bit, I'll take 6h over rho d cp. Sounded like I was on Jeopardy. I'll take 6h over rho dp for 1,000, please. All right, so once you plug in all the numbers, once again, I won't do this in the interest of time, but h is just this convective heat transfer coefficient, rho is just this density here, diameter is geometry, cp is the heat capacity, it's right here. Make sure all the units come out, and b comes out to 0.0154 inverse seconds. And looking at my units here, it looks like there's there's a kilojoule per second to watt conversion, so you might want to try it on your own, make sure you see that little conversion factor, but it's pretty straightforward. So we've got the value of b now. So if you plug in the value of b, which is 0.0154,
The 1 over s is a unit, right?
yes, inverse seconds, that's right, that's a unit. Good question. So if you plug that in here, you plug in the temperature as a function of time. What would I plug in there? Temperature as a function of T. I'm looking for the particular time when the body has reached this temperature. What temperature is that?
100C.
100C, that's right. What's T infinity again?
35C.
35C, the temperature of the air. What's TI? Initial temperature of the body, 900. Good. So you plug all that in, you'll find the amount of time required comes out to 168 seconds, which is about 2.8 minutes. Okay. So 2.8 minutes down the line, the balls have gone from 900 to 100.
Where inside that T equals equation is B?
This is right here.
Oh, okay.
It's in the denominator. Now, that wasn't the only thing they asked. They asked us to find the rate of heat transfer from the balls. Okay, so if we process 2,500 balls per hour, how much heat are we going to have to suck out? Because think about it. I mean, if you got steel balls at 900 degrees going down to 100 degrees, and you got 2,500 of those flowing through every hour, and it's summertime outside, we may end up cooking some people, right, that are working the line. That would be bad. So we need to know how much ventilation we need to get rid of this excess heat. Now, in the wintertime, it might be helpful. We may be able to heat the plant with this. Who knows? Let's find out. Let's see what happens. Let's see. I think we're done with this bit over here. So let me just start over up at the top. So for part B, we'd like to know the heat transfer rate when we're processing 2,500 balls per hour. Well, here's what I'm going to do. I'm going to calculate how much heat each ball loses. And if I'm processing 2,500 balls an hour, then I can figure out the heat flow rate from all of them. Does that make sense? So if I know how much, you think of these as buckets of water. If I know how much volume of water each of the buckets contribute, and I know how many buckets are flowing through hour, I can tell you the flow rate of the water, right? It's just the volume multiplied by the flow rate. So the amount of heat, notice I'm not writing Q dot, I'm talking about just the amount of energy one ball goes off. It's mCp delta T, where this would be the temperature less the initial temperature. Okay? So the ball goes from 900 down to 100, and I'd like to know how much heat transfer that represents. Now I should, to get Q to be positive, I just noticed in my notes I should switch these around. The initial temperature is higher than the final temperature. So let me write it that way so it's obvious Q is coming out in positive. Okay. But the mass, I don't know. In fact, the mass would be density times volume. Right? M equals rho V. You should know that by now. If you don't, it's okay. Just make a note that you can use the mass and, or you can use, excuse me, the density and volume to get mass. Just make a note of that. And by the way, the volume of this thing would be pi d cubed over 6. Same thing as 4/3 pi r cubed. The volume of a sphere. I won't plug it in for you here. You can do that at home. This is 2.68 times 10 to the negative 7th cubic meters of steel per ball. Okay, so that's just the volume of one of the balls. So if you plug in the density that was given, the volume that we just calculated, the heat capacity, and what initial temperature again?
900 C.
What final temperature? 100, good. When you plug all that in, you find that the amount of heat that each ball gives off is 0.781 kilojoules. So each ball gives off 0.781 kilojoules. Okay. Now, the heat flow rate into the air would be equal to the heat that each ball gives off times the number of balls per time, right? Which is 2,500 balls per hour. See how we get kilojoules per hour, which is a power, it's a flow rate? Well, this comes out to about 1953 kilojoules per hour. Now, that's not very convenient. We'd like to get kilowatts. And so if you convert it, you convert the hours into seconds, you come up with about 0.542 kilowatts. So it's about 500 watts or so. Are we gonna heat the factory with 500 watts? No. Anybody ever use work lights, halogen work lights? Okay, each bulb is about 250 watts. If you have a dual-headed lamp, you got about 500 watts there. So this is probably not enough to really heat up much, right? So we wouldn't have to worry about it. Okay, now let's go and let's analyze this problem a different way. We still have a little bit of time. So let's analyze it using the Heisler-Grover charts, and then we'll plug in the equations and see what we get. Okay. Now, which model should I use? The plane, wall, cylinder, or sphere? Sphere. It's obvious, right? I should definitely use the sphere. What do I need to do in order to use the model for the sphere? Well, I need a BO number. Wait a second, didn't I have a BO number a minute ago? Well, this BO number has to be based on the radius of the sphere, not the diameter over 6 or not the radius over 3. So let me calculate the BO number again, but this is the BO number for the model, not the BO number for deciding whether or not to use the model. Okay? So that would be, let's see, let's get everything together. In fact, why don't you guys look it up? You need to anyway. Look up the BO number. How do I calculate it?
Same way we did before, except plug in R over 3 for,
Right, so what do I write down here?
that's 75.
H
R
over K, that's right. Okay, so I'll need some calculator help because I haven't finished this obviously. This time we'll actually plug everything in. H, 75 watts per square meter per degree Celsius. R, let's see, we were given the diameter of the balls, but I neglected to write it down.
It's 8 millimeters.
Yeah, I thought it was 8 millimeters. So the diameter is 0.008 meters. 1, 2, 3. Therefore, the radius would be half that, so that'd be 0.004 meters. Divided by K, the thermal conductivity, 54 watts per meter per degree Celsius. Do all the units go away? Degrees Celsius, watts, yes. And yes, meters will go away. So we have a non-dimensional number before, which we did before, so this is good. So what's the BO number?
0.0055.
0.0055, okay. Now to use the charts, what I like to do is instead of going directly to the equations, I like to use the charts to begin, because if I use the charts, then I can get approximately in the ballpark, right? And then when I use the equations, I can tell whether or not I've made a mistake along the way, okay? The charts are easier to use, so I prefer to use those. Now, the problem is that we've got to ask the question, well, what temperature are we talking about here, this 100 degrees Celsius? Is that the surface temperature? Is it the center line temperature? What is this? Let's say it's the center temperature, okay? Because theoretically, the surface temperature is going to drop to 35 degrees very, very quickly, okay? So let's just say that temperature is now the center line temperature, okay? So here's our BO number. Now to use the charts, we'll have to take 1 over the BO number. So since you've got it in your calculator, just go ahead and invert it and give me a number here. What is the inverse of this BO number?
180.
180? Notice both of these are non-dimensional. Okay? Now, let's go into the Heisler-Grover charts and see if we can look things up. Now, this is the supplementary document that I've posted with the homework. And the sphere is last. It should be, well, I guess I went past it. This must be the sphere. Yeah, center temperature is a function of time in a sphere of radius R0. Okay. Now, unfortunately, it looks like we're going to run into a roadblock here because the BO number that we've got here is 180. This chart only goes up to 100, the inverse of the BO number. So I guess we'll give up on this because we have 15 minutes and we could move on to the next example problem.
Doesn't it say 250 at the end, in the corner?
That is the Fourier number on the x-axis. The BO number
Oh.
numbers are up here, or inverse of BO numbers are up here. And it only goes to 100, so. All right.